Every night, somewhere above you, invisible threads of gravity pull at distant worlds. Right now, at this very moment, you are traveling through space at over 80,000 kilometers per hour, carried along by a cosmic tide so vast it takes roughly 230 million years to complete a single turn. You are part of a spiral, a pinwheel of light, a home woven from the remnants of ancient stars and threaded through with darkness we cannot see. The Milky Way galaxy is not just a backdrop to your life. It is the stage itself. Every atom in your body was forged inside a star that burned and died before the Earth was born. The calcium in your bones, the iron in your blood, the carbon that forms every cell, all of it came from explosions that scattered their gifts across the void. You are made of stardust, not as metaphor, but as fact. And tonight, we will drift together through the vast and luminous spiral that made you possible. Perhaps you had a long day. Perhaps your thoughts are too loud, or the silence feels too heavy. Either way, you are here now, and there is nowhere else you need to be. Let your shoulders soften. Let your breath slow. The galaxy has been turning for over 13 billion years, and it will keep turning long after this moment has passed. All you need to do is rest. Welcome to the Sleepable Science channel. I'm so glad you found your way here. If you enjoy these gentle explorations into the mysteries of our universe, consider liking and subscribing. It helps others find their way to this quiet corner of curiosity. But for now, let's begin. We are about to drift through 100 facts about the Milky Way, each one a small window into the grandeur and strangeness of our galactic home. Some will surprise you, others will settle in like old friends. And through it all, I hope you find a kind of peace in knowing just how vast and wondrous this place truly is. Now, close your eyes if you'd like, let your mind wander, and together let us float through the Milky Way, one quiet fact at a time. The architecture of home. The Milky Way is a barred spiral galaxy, a cosmic pinwheel stretching approximately 100,000 light-years from edge to edge. To grasp this distance, imagine light itself, the fastest thing in the universe, racing at 300,000 kilometers per second, traveling for 100,000 years without stopping. That is the width of our home, not a small village, but an empire of stars. And within this empire, there are citizens. Between 200 and 400 billion stars call the Milky Way home, each one a sun in its own right, many with their own families of planets. Some are newborns, blazing hot and blue, their fierce radiation carving out cavities in the nebulae that birthed them. Others are ancient, cool and red, having witnessed the rise and fall of entire star systems, burning steadily for billions of years. And somewhere among them, about 26,000 light-years from the galactic center, in a quiet suburb of the spiral, orbits a modest yellow star we call the Sun. Neither the brightest nor the dimmest, neither the youngest nor the oldest. An ordinary star in an extraordinary galaxy. The galaxy is not flat like a dinner plate, though it appears that way from certain angles. It is more like a pancake, with a bulge in the middle and a gentle warp at the edges. The disk itself, the main body where most stars reside, is only about 1,000 light-years thick. Thin, in cosmic terms. A ratio more extreme than the thinnest crepe. But within that thin slice lies an astonishing density of matter, gas, dust, planets, asteroids, comets, and the quiet spaces between. It is in the disk that most of the action happens, where stars are born, where they live, where they die. At the center of the disk sits the galactic bulge, a dense spherical swarm of ancient stars roughly 10,000 light-years across. These stars are older than the disk itself, born in the galaxy's infancy. when the universe was still young and wild. They orbit the galactic core in chaotic paths, not the orderly circles of the disk, but ellipses and loops that carry them through the heart of the Milky Way again and again. The bulge glows with a warm, yellow-orange light, the light of old stars that have been burning for billions of years. The spiral arms, those graceful arcs of light that define the galaxy's shape, are not solid structures. They are density waves, regions where stars, gas, and dust gather temporarily before moving on. Think of them as traffic jams in space. The stars do not stay in the arms forever. They drift in and out, swept along by gravity's invisible currents. But in those arms, something remarkable happens. The compression of gas and dust triggers star formation. New suns ignite. Stellar nurseries bloom. The arms are not just beautiful, they are productive, birthing new generations of stars from the debris of the old. Recent observations from NASA's Spitzer Space Telescope have revealed that the Milky Way has two major spiral arms, the Perseus and Scutum-Cestorus arms, and two minor arms, the Sagittarius and Norma arms. Our Sun resides in neither of these grand structures. Instead, we live in a smaller, partial arm called the Orion Spur, a branch that connects the larger arms like a tributary between rivers. It is a quieter region, less dense with stars, less dramatic in its star formation. A peaceful neighborhood in the cosmic suburbs. From our vantage point, deep within the disk, we cannot see the Milky Way's full structure. We look along the plane, not down upon it. The result is that hazy river of light stretching across the night sky, a sight that has inspired wonder and myth since humans first looked up. The ancient Greeks called it the Milky Circle. The Romans, Via Lactea, the Milky Road. Indigenous peoples around the world saw it as a pathway for souls, a river in the sky, a bridge between worlds. We see the galaxy from the inside, like standing in a forest and trying to imagine its shape from the trees. But we are not just passive observers. Missions like Gaia, launched by the European Space Agency, have measured the positions, distances, and motions of nearly 2 billion stars, creating the most detailed three-dimensional map of the galaxy ever made. Slowly, painstakingly, we are learning the Milky Way's true form. And what we have learned is this: the galaxy is not symmetrical. One side of the disk is slightly thicker than the other. The spiral arms are uneven in brightness and extent. Even the stellar halo, the diffuse cloud of old stars and globular clusters that surrounds the disk, is elongated and tilted, stretched like a rugby ball rather than a sphere. These asymmetries are the scars of the galaxy's history, the marks left by ancient collisions and the ongoing tug of dark matter and neighboring galaxies. The Milky Way is not a perfect structure. It is a living, changing system, shaped by forces seen and unseen, by the past and the present colliding in slow motion across billions of years. It is imperfect, lopsided, warped at the edges. And in that imperfection lies its beauty. Surrounding the visible disk and bulge is the galactic halo, a vast spherical region extending perhaps 130,000 light-years or more from the center. The halo is sparsely populated compared to the disk. Only a few scattered stars and ancient globular clusters, spherical collections of hundreds of thousands of stars bound tightly by gravity. These globular clusters are some of the oldest structures in the galaxy, formed over 12 billion years ago when the Milky Way was still coalescing from primordial gas clouds. They orbit the galactic center on long, swooping paths that carry them high above and below the disk, like celestial moths circling a lamp. Each globular cluster is a relic of the early universe, a time capsule preserving conditions from the galaxy's youth. The stars within them are metal poor, composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements. This tells us they formed before successive generations of supernovae had enriched the galaxy with carbon, oxygen, and iron. Looking at a globular cluster is like looking back in time, seeing the galaxy as it was when it was young. But the halo contains more than just stars. It is also the domain of dark matter, the invisible substance that makes up roughly 85% of the galaxy's total mass. We cannot see dark matter. It does not emit, absorb, or reflect light. Yet its presence is undeniable, revealed through its gravitational effects on the motion of stars and gas. The dark matter halo is what holds the galaxy together, a hidden scaffold that keeps the spiral from flying apart as it spins. And the Milky Way does spin. The entire galaxy rotates around its center, though not like a solid wheel. Different parts rotate at different speeds. Stars near the center complete their orbits much faster than those on the outskirts. Our Sun, traveling at an average speed of 828,000 kilometers per hour, takes approximately 230 million years to complete one orbit, a period sometimes called a galactic year. Since the Sun and Earth formed about 4.6 billion years ago, we have completed roughly 20 orbits around the galaxy. Dinosaurs walked the Earth just one galactic year ago. Interestingly, the Sun has not remained at the same distance from the galactic center throughout its lifetime. Evidence from its chemical composition suggests it formed closer to the center, perhaps around 16,000 light-years from the core, and has since migrated outward through a process called radial migration. Stars gradually shifting along spiral arms, pushed by gravitational interactions over billions of years. The galaxy is also warped. For decades, astronomers have known that the disk does not lie perfectly flat. Near the edges, it curves upward on one side and downward on the other, like the brim of a fedora hat tilted at an angle. The warp can extend as much as 20,000 light-years above or below the main galactic plane. Current evidence suggests this distortion is caused by the gravitational influence of nearby satellite galaxies, particularly the Magellanic Clouds, two small irregular galaxies that orbit the Milky Way like cosmic companions. The Milky Way, then, is not a single isolated island. It is part of a larger structure, a neighborhood of galaxies bound together by gravity. This neighborhood is called the Local Group, and it contains more than 80 known galaxies, including our own, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. Together, these galaxies orbit a common center of mass, engaged in a slow, gravitational dance that has been ongoing for billions of years. And in time, this dance will change. The Milky Way is not static. It is still growing, still evolving, still absorbing smaller galaxies and being shaped by collisions yet to come. It is a structure in motion, a spiral caught between the past and the future, turning slowly through the dark. The heart of darkness. At the very center of the Milky Way, hidden behind thick clouds of gas and dust, lies something extraordinary, something massive, something quiet yet powerful beyond imagining. It is a supermassive black hole, and its name is Sagittarius R. Sagittarius A, often abbreviated as GR, sits approximately 26,000 light-years from Earth, nestled in the direction of the constellation Sagittarius near the galactic core. It was first detected as a radio source in 1974, a compact, bright point of emission unlike anything else in the region. For decades, astronomers could not see it directly. The dense clouds of interstellar dust that clog the galactic center block visible light, turning the core into an opaque wall. but radio waves pass through dust with ease, and in radio wavelengths, SGRA shines brightly. By observing the orbits of stars near the galactic center, astronomers gradually pieced together the black hole's properties. Stars like S2, one of the fastest-moving stars known, orbit SGRA in tight elliptical paths, reaching speeds of up to 5,000 kilometers per second, nearly 2% the speed of light. By measuring these orbits with exquisite precision, scientists calculated the mass of the object at the center. The numbers were staggering. It's a mass of approximately 4.3 million times that of our Sun, all confined within a region no larger than the distance between the Sun and Mercury. There is only one explanation for such an object: a supermassive black hole. Black holes are regions of space-time where gravity is so strong that not even light can escape. They form when massive stars collapse at the end of their lives. But supermassive black holes like SGRA are different. They are millions or even billions of times more massive than stellar black holes, and they reside at the centers of most large galaxies. How they form remains an active area of research, though astronomers have developed several theories. They may have grown over billions of years by consuming gas, dust, and entire stars, or by merging with other black holes during galactic collisions. Some researchers propose they could have formed from the direct collapse of massive gas clouds in the early universe, while others suggest they grew from smaller seed black holes. The exact mechanism likely varies, and multiple processes may have contributed to their formation. SGRA is relatively quiet compared to other supermassive black holes. Many galactic centers are active, with matter spiraling inward at high speeds, heating up and emitting intense radiation as it falls toward the event horizon. These active galactic nuclei can outshine entire galaxies. But SGRA is quiescent. It consumes matter slowly, almost gently, like a slumbering giant. If Sagittarius A were the size of a human, it would consume the mass of a single grain of rice every million years. Yet it is not entirely dormant. In 2022, astronomers using the Event Horizon Telescope, a global network of radio observatories working together as a single Earth-sized telescope, captured the first image of Sagittarius A. The image shows a bright ring of light surrounding a dark central region. This is not the black hole itself, which by definition cannot be seen, but rather the glowing gas that orbits just outside the event horizon. The light from that gas, bent and twisted by the black hole's immense gravity, forms a luminous halo around a shadow, the first direct visual evidence of the black hole at the heart of our galaxy. The event horizon of the boundary beyond which nothing can escape, has a diameter of approximately 24 million kilometers, roughly the distance from the Sun to Mercury. Inside that boundary, space-time is so warped that all paths lead inward. Time itself behaves strangely. According to general relativity, an observer falling toward the black hole would experience time slowing down, relative to someone far away. At the event horizon, from an outside perspective, time would effectively stop, though the falling observer would not notice anything unusual, until they crossed the boundary and, theory predicts, would be torn apart by tidal forces so extreme that even atoms could not remain intact. Around the event horizon lies the accretion disk, a swirling maelstrom of gas and dust heated to millions of degrees as it spirals inward. The material in the accretion disk glows in multiple wavelengths, from radio waves to X-rays, making the black hole detectable even though it remains invisible. Occasionally, SGRA flares, brightening suddenly as clumps of matter fall into it. These flares have been observed in X-ray, infrared, and radio wavelengths, revealing the chaotic, dynamic environment near the event horizon. Recent studies using NASA's Imaging X-ray Polarimetry Explorer (IXPE) and the Chandra X-ray Observatory have uncovered something remarkable. Approximately 200 years ago, a blink of an eye in cosmic terms, Sagittarius A underwent a powerful outburst, devouring a large amount of matter and releasing intense X-ray radiation. The evidence for this ancient flare comes from nearby molecular clouds, massive clouds of gas that now glow faintly in X-rays. These clouds are essentially reflecting the light from that long-ago event, like echoes bouncing off distant walls. The discovery suggests that Sagittarius has not always been as quiet as it appears today. It has episodes of activity, feeding frenzies followed by long periods of rest. The existence of Sagittarius A has profound implications for our understanding of the galaxy. The black hole's gravity influences the motion of stars throughout the galactic bulge. It shapes the orbits of gas clouds and helps regulate the flow of matter through the galactic center. Research increasingly suggests that supermassive black holes may play a crucial role in galaxy formation and evolution, potentially acting as gravitational anchors around which galaxies coalesce and helping to regulate star formation through energetic feedback. However, untangling these complex relationships remains an active area of investigation. In 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for their discovery that Sagittarius A is a supermassive compact object, work that spanned decades of painstaking observation. Their research provided overwhelming evidence that the object at the center of the Milky Way could only be a black hole, confirming what many had suspected, but none had definitively proven. And yet, despite all we have learned, Sagittarius A remains profoundly mysterious. What lies beyond the event horizon remains one of physics' deepest questions. Current theories suggest that matter crossing this boundary would be subjected to forces so extreme that even atoms could not remain intact. Whether information is truly lost or somehow preserved, perhaps encoded on the black hole's surface, as some theories propose, remains hotly debated among physicists. These are questions that probe the very limits of our understanding, touching on the nature of space-time, quantum mechanics, and the ultimate fate of matter in the universe. For now, Sagittarius sits quietly at the heart of the Milky Way, a dark sentinel holding the galaxy together with invisible threads of gravity. It is both a monument to the past and a harbinger of the future, a reminder that even in the quietest corners of the cosmos, there are forces at work beyond our comprehension. And we, floating on a small planet in a modest solar system, are bound to it. Every star in the galaxy, including our Sun, dances to the gravitational music of Sagittarius A. We are all children of the galactic center, swept along in its slow, majestic orbit. A galaxy in motion. Nothing in the universe stands still. The Earth spins on its axis, completing one rotation every 24 hours. The Earth orbits the Sun, tracing an ellipse through space once every 365 days. But the Sun itself is not stationary. It is moving, and so is everything around it. The entire solar system is in motion, carried along by the rotation of the Milky Way, sweeping through space at speeds that defy easy comprehension. Our Sun, along with all its planets, moons, asteroids, and comets, orbits the center of the Milky Way at an average velocity of 828,000 kilometers per hour, or about 230 kilometers per second. That is fast enough to travel from the Earth to the Moon in just 1 hour. And yet, despite this incredible speed, the Sun's orbit is so vast that it takes approximately 230 million years to complete a single lap around the galaxy. This period is sometimes called a galactic year, or a cosmic year, and it provides a humbling sense of scale. Think about it this way. The last time the Sun was in its current position in the galaxy, the Earth was a very different place. Dinosaurs had not yet evolved. The continents were arranged differently. The climate was warmer, and the oceans teemed with ancient life forms that would soon give rise to the age of reptiles. One galactic year ago, the world looked nothing like it does today. Since the Sun and Earth formed roughly 4.6 billion years ago, the solar system has completed about 20 orbits around the Milky Way. 20 galactic years. In that time, stars that were once nearby have drifted away, replaced by new neighbors. The constellations we see today will not be the same constellations our distant descendants see millions of years from now. The stars are not fixed. They are all moving, each following its own path through the galaxy. The Sun's orbit is not perfectly circular. Like the planets orbiting the Sun, the solar system follows an elliptical path around the galactic center, influenced by the gravitational pull of the central bulge, the spiral arms, and the dark matter halo. But there is another motion as well, a bobbing up and down, perpendicular to the galactic plane. As the Sun travels along its orbit, it also oscillates above and below the disk, crossing the galactic plane approximately every 30 million years. Some researchers have explored whether this oscillation might have consequences for life on Earth, hypothesizing that when the solar system passes through the denser regions of the galactic plane, it could encounter more dust and debris. However, establishing clear connections between these passages and specific climate or extinction events on Earth remains challenging, and this area continues to be studied. Our location in the galaxy is not random. The Sun resides in the Orion Spur, a minor spiral arm situated between two major arms, the Perseus arm to the outside and the Sagittarius arm toward the galactic center. We are about 26,000 light-years from the center, roughly halfway out toward the edge of the disk. If the Milky Way were a city, we would be living in the suburbs, far from the crowded, chaotic core, but not quite in the rural outskirts. This location is significant. The inner regions of the galaxy are harsher. Stars are packed more densely, increasing the likelihood of close encounters and gravitational disruptions. Supernovae are more frequent, bathing nearby systems in radiation. Near the galactic center, the intense radiation from Sagittarius A and the high density of stars could make planetary systems unstable and less hospitable to life as we know it. On the other hand, the outer regions of the galaxy are calmer but also poorer in heavy elements, the building blocks of rocky planets and organic molecules. This has led some astronomers to propose the idea of a galactic habitable zone, a ring-shaped area of the galaxy where conditions might be more favorable for life to emerge and persist. The Sun sits within this proposed zone, a cosmic middle ground where the conditions are neither too harsh nor too barren. But our galaxy does not orbit in isolation. The Milky Way itself is moving, carried along by the expansion of the universe and the gravitational pull of nearby structures. The local group, the collection of galaxies to which the Milky Way belongs, is being drawn toward a massive concentration of galaxies called the Virgo cluster, part of an even larger structure known as the Laniakea supercluster. In this grand cosmic dance, everything is in motion, from the smallest atom to the largest galaxy cluster. As the Sun moves through the galaxy, it also moves through different regions of the interstellar medium, the thin gas and dust that fills the space between stars. Currently, the solar system is traveling through a region called the local bubble, a relatively empty cavity blown out by ancient supernova explosions. The local bubble is about 1,000 light-years across and significantly less dense than the surrounding interstellar medium. But this was not always the case. In the past, the Sun may have passed through denser regions, encountering clouds of gas and dust that could have affected the solar wind, the heliosphere, and even the climate on Earth. It is strange to think that our journey through the galaxy is not just a passive drift. The solar system is an active participant in the galaxy's life, moving through different neighborhoods, encountering different conditions, shaped by the forces around it. The Sun is not just a star. It is a traveler, a wanderer, carrying its family of planets through the vast expanse of the Milky Way. And we are passengers on that journey. Every moment, every breath, we are hurtling through space, spinning on a planet that orbits a star, that orbits a galaxy, that itself is moving through the cosmos. It is a motion so smooth and constant that we do not feel it. But it is there, always a quiet reminder of the vastness in which we live. The galaxy turns, the sun moves, and we move with it, small and fragile, yet part of something immense. The invisible embrace. Most of the Milky Way is invisible. This is not a poetic exaggeration. It is a simple, profound truth. When we look at the night sky, we see stars, glowing gas clouds, the faint smudge of distant nebulae. But all of this, the entire luminous galaxy, represents only a small fraction of the Milky Way's total mass. The rest is dark matter, an invisible substance that permeates the galaxy like a hidden skeleton, holding it together in ways we are only beginning to understand. Dark matter does not emit light, does not absorb it, does not reflect it. It interacts with ordinary matter almost exclusively through gravity. We cannot see it, cannot touch it, cannot detect it with any conventional instrument. Yet its presence is undeniable. In the 1970s, astronomer Vera Rubin measured how stars move in spiral galaxies. She expected to find that stars farther from the center orbit more slowly, just as outer planets orbit the sun more gently than inner ones, a natural consequence of distance and gravity. But the stars refused to cooperate. The ones at the edges were moving just as fast as those near the center, sometimes faster, as if held in place by something unseen. The only explanation? Vast halos of invisible matter wrapping around galaxies like cocoons. In the Milky Way, this dark matter halo contains at least 10 times as much mass as all the visible stars combined. Perhaps more. It is the hidden majority, the invisible embrace that keeps the galaxy from flying apart. The dark matter halo surrounding the Milky Way is enormous. It extends at least 300,000 to 400,000 light-years from the galactic center, far beyond the visible disk, far beyond the stellar halo. Some estimates suggest it may reach even farther, perhaps 500,000 light-years. This means the Milky Way is not just a spiral of stars. It is a small, bright island floating within a vast, invisible ocean of dark matter. The halo is not perfectly round. Recent studies using data from the Gaia mission suggest it is elongated, tilted, shaped more like a rugby ball than a sphere. This asymmetry likely reflects the galaxy's complex history, shaped by past mergers with smaller galaxies and the ongoing gravitational tug of nearby structures. The total mass of the Milky Way, visible matter and dark matter combined, is estimated somewhere between 1 trillion and 1.5 trillion solar masses. Of this, only about 10 to 15% takes the form of stars, gas, and dust. The stuff we can see. The rest is darkness. We live in a galaxy whose very existence depends on something we cannot observe directly. But what is dark matter? This is one of the greatest unsolved mysteries in modern physics. Scientists have proposed many candidates. Some theories suggest dark matter could be composed of weakly interacting massive particles, WIMPs, exotic particles that would interact only through gravity and the weak nuclear force. Others propose axions, hypothetical particles predicted by certain theories but never detected. Still others wonder if dark matter might be something even stranger, perhaps pointing toward modifications of gravity itself, rather than new particles. Each possibility has its proponents, but definitive evidence remains elusive. Despite decades of searching, no one has conclusively detected a dark matter particle. Experiments deep underground, shielded from cosmic rays, have looked for the faint signals that might indicate a dark matter interaction. So far, they have found nothing conclusive. The dark matter remains elusive, a ghost in the machine of the cosmos. Yet the evidence for its existence is overwhelming. Beyond the motion of stars, dark matter reveals itself through gravitational lensing, the bending of light from distant objects by the gravity of foreground mass. When astronomers look at galaxy clusters, they see the light from background galaxies distorted into arcs and rings, evidence of vast amounts of unseen mass bending space-time. The distribution of this lensing matches the predictions of dark matter models with remarkable precision. Dark matter also plays a crucial role in the formation of galaxies. In the early universe, shortly after the Big Bang, observations and models suggest that dark matter began to clump together under the influence of gravity, forming large-scale structures, cosmic webs of filaments and halos. Ordinary matter, composed of hydrogen and helium, was too hot at first to collapse on its own. But it was drawn into the gravitational wells created by dark matter, cooling and condensing into gas clouds that eventually formed the first stars and galaxies. Without dark matter, according to current cosmological models, galaxies as we know them could not have formed. The universe would be a very different, and likely barren, place. In the Milky Way, dark matter continues to shape the galaxy's evolution. It provides the gravitational scaffolding that holds the spiral arms in place and prevents stars from flying off into intergalactic space. It influences the orbits of satellite galaxies like the Magellanic Clouds, and it may even play a role in triggering waves and disturbances in the galactic disk. Some recent research has suggested that the dark matter in the inner galaxy may not be distributed in a simple spherical halo. Instead, observations hint it may be flattened and aligned with the disk of stars, forming a structure more complex than previously thought. If confirmed, this could help explain a long-standing puzzle: the excess of gamma rays observed from the galactic center. One hypothesis proposes these high-energy photons might result from dark matter particles colliding and annihilating each other, releasing energy in the process. This remains an active area of investigation, with researchers working to distinguish such signals from more conventional sources like pulsars or cosmic ray interactions. The dark matter halo is not static. It is constantly being disturbed by the motion of satellite galaxies, by the gravitational influence of the galactic bar, by the ongoing accretion of gas and smaller dark matter structures from the intergalactic medium. In some ways, the halo is like a living thing, breathing, shifting in response to the forces acting upon it. And within that halo, nested like a pearl in an oyster, sits the luminous galaxy. The stars, the gas, the planets, the life. All of it held in place by the invisible embrace of dark matter. We do not know what dark matter is. We cannot see it or touch it, but we can feel its effects, written in the motion of stars and the structure of galaxies. It is a reminder that the universe is far stranger and more mysterious than it appears. Most of what exists is hidden from us, present but unseen, shaping our reality in ways we are only beginning to comprehend. The Milky Way is not just what we see, it is what we cannot see. The dark scaffold that holds the light. Stellar nurseries and birth stars are born in darkness. Not the darkness of space, which is actually quite bright with starlight, but the thick, cold darkness of molecular clouds. Vast regions of gas and dust so dense that they block out all light. These clouds, often called stellar nurseries, are the birthplaces of stars. They are where the raw material of the universe collapses under its own weight, igniting nuclear fusion and bringing new light into the cosmos. The Milky Way is dotted with stellar nurseries, scattered throughout its spiral arms. Some are small, containing only enough matter to form a handful of stars. Others are enormous, spanning hundreds of light years and containing enough material to form hundreds of thousands of stars. These giant molecular clouds are among the most massive structures in the galaxy, with masses ranging from 1,000 to 10 million times that of the Sun. Molecular clouds are cold, typically only about 10 to 20 degrees above absolute zero. At these temperatures, gas molecules move slowly, and gravity can begin to pull them together. But gravity alone is not enough. The clouds are held up by internal pressure, magnetic fields, and turbulence. For a cloud to collapse and form stars, something must disturb it. A shockwave from a nearby supernova, the gravitational tug of a passing star, or the compression caused by the spiral density wave of the galactic arms. When a molecular cloud is disturbed, parts of it begin to collapse. These collapsing regions, called cores, grow denser and hotter as gravity pulls more material inward. Eventually, the core becomes so hot and dense that hydrogen atoms begin to fuse into helium, releasing vast amounts of energy. A star is born. The process is not instantaneous. It can take millions of years for a molecular cloud core to collapse and ignite fusion. During this time, the protostar, the infant star, is hidden from view, surrounded by a cocoon of gas and dust. The light it emits is absorbed by the surrounding material and re-radiated as infrared radiation, which can pass through the dust more easily than visible light. This is why infrared telescopes, like NASA's James Webb Space Telescope, are so valuable for studying star formation. They can see through the dust and reveal the protostars hidden within. Most stars do not form in isolation. They are born in clusters, dozens or even thousands of stars emerging from the same molecular cloud within a relatively short time. These stellar clusters are bound together by gravity, at least initially. Over time, interactions between stars can cause some to be ejected from the cluster, while others remain bound. The Pleiades, a famous star cluster visible to the naked eye, is one such group, a collection of young, hot stars still wrapped in the faint wisps of the nebula from which they formed. The Milky Way contains many famous star-forming regions, each one a laboratory for studying how stars are born. The Orion Nebula, located about 1,550 light-years from Earth, is one of the closest and most well-studied. It is a vast cloud of gas and dust illuminated by the intense radiation of young, massive stars. Within the nebula, astronomers have detected hundreds of protostars at various stages of development, from tiny cores just beginning to collapse to fully formed stars clearing away their natal cocoons. On a dark winter night, you can see the Orion Nebula with the naked eye, a faint smudge in the sword of Orion, a cosmic nursery visible across 1,150 years of space and time. Another prominent star-forming region is the Carina Nebula, about 7,500 light-years away. This nebula contains some of the most massive and luminous stars in the galaxy, including Eta Carinae, a star so massive and unstable that it could explode as a supernova at Endor time. The Carina Nebula is also home to towering pillars of gas and dust, sculpted by the intense radiation and stellar winds of nearby stars. These pillars are themselves sites of active star formation. with new stars being born even as older stars tear the nebula apart. It is a place of creation and destruction, happening simultaneously, in slow motion, over millions of years. The Gaia mission has revolutionized our understanding of star-forming regions by creating the first accurate three-dimensional maps of stellar nurseries within 4,000 light-years of the Sun. By measuring how light from stars is dimmed by dust, a process called extinction, Gaia can infer the location and density of dust clouds. When combined with observations of massive O-type stars, which emit intense ultraviolet radiation that ionizes nearby hydrogen gas, Gaia's maps reveal the shapes, cavities, and structures of stellar nurseries in unprecedented detail. One surprising discovery from these maps is that some star-forming regions appear to have broken open, with streams of gas and dust venting into giant cavities. These cavities are likely created by the powerful radiation and stellar winds from massive young stars, which can blow away the surrounding material and carve out empty spaces in the molecular clouds. This process, known as feedback, limits the efficiency of star formation. Without feedback, molecular clouds would convert all their gas into stars within a few million years. Instead, only a small fraction, perhaps 1 to 10% of a cloud's mass, becomes stars. The rest is dispersed back into the interstellar medium. The galaxy breathes. It takes in gas, forms stars, and exhales the remainder, enriched with new elements, back into the cosmic ecosystem. Star formation is not a uniform process. It varies across the galaxy, concentrated in the spiral arms where gas and dust are compressed by density waves. In the inner regions of the galaxy, star formation is more vigorous, fueled by a higher density of gas. In the outer regions, it is slower and more sporadic. But even in the outskirts, new stars are born, adding to the galaxy's population. The rate at which the Milky Way forms stars, its star formation rate, is estimated to be about 1 to 2 solar masses per year. That means every year, the equivalent of 1 or 2 suns' worth of gas is converted into new stars. It may not sound like much, but over billions of years, it adds up. Most of the stars in the galaxy were formed in the distant past, during a period of intense star formation billions of years ago. Today, the rate has slowed, and the Milky Way is what astronomers call a mature galaxy, no longer in the throes of its youth, but still producing new generations of stars. The life cycle of stars is intimately connected to the life cycle of the galaxy. When massive stars die, they explode as supernovae, scattering heavy elements, carbon, oxygen, iron, and others, into the interstellar medium. These elements enrich the gas clouds from which new stars form, creating a feedback loop in which each generation of stars is slightly more metal-rich than the last. The Sun, for instance, formed about 4.6 billion years ago from a cloud that had already been enriched by previous generations of stars. The heavy elements in that cloud, elements forged in the cores of ancient stars and scattered by their deaths, eventually became the rocky planets of the solar system, including the Earth and everything on it. Star formation, then, is not just the birth of light. It is the engine of cosmic evolution, the process by which the universe creates complexity and diversity. From simple hydrogen and helium, star formation builds the periodic table, one supernova at a time. And within those stellar nurseries, hidden in the cold and the dark, the future of the galaxy is being written. New stars are being born. New planetary systems are taking shape. And perhaps somewhere among them, life is beginning again, as it once did here. Ancient collisions and future mergers. The Milky Way is not an isolated island. it is part of a cosmic ecosystem, constantly interacting with its neighbors. Over billions of years, the galaxy has consumed smaller galaxies, absorbed their stars, and scattered their remnants across the sky. And in the future, it will merge with another large galaxy, transforming both into something entirely new. The evidence for past mergers is written in the stars themselves. By analyzing the chemical composition and motion of stars in the Milky Way, astronomers have discovered that not all stars were born here. Some have chemical signatures that do not match the rest of the galaxy, suggesting they originated in smaller galaxies that were later absorbed. Others move in retrograde orbits, circling the galactic center in the opposite direction from most stars, a telltale sign of a foreign origin. One of the most significant past mergers occurred about 10 billion years ago, when a dwarf galaxy known as Gaia Sausage Enceladus collided with the Milky Way. This ancient galaxy contained roughly 600 million solar masses of stars and contributed significantly to the formation of the Milky Way's stellar halo and thick disk. The collision was violent, sending stars into elongated, tilted orbits and disrupting the structure of the young Milky Way. Today, the remnants of Gaia Sausage Enceladus can still be seen in the motion of stars in the halo, ghostly streams moving in directions that defy the galaxy's orderly rotation. But Gaia Sausage Enceladus was not the only victim. Over its lifetime, the Milky Way has devoured dozens of smaller galaxies, some of which are still in the process of being torn apart. The Sagittarius Dwarf Galaxy, for instance, is currently colliding with the Milky Way, passing through the galactic disk and being stretched into long tidal streams by the Milky Way's gravity. These streams wrap around the galaxy like ribbons, marking the path of the dwarf galaxy's orbit. In a few 100 million years, the Sagittarius dwarf will be completely disintegrated, its stars scattered and merged with the Milky Way. Other satellite galaxies, like the Large and Small Magellanic Clouds, may also be on trajectories that could lead to interactions with the Milky Way, though their precise future remains uncertain. The Magellanic Clouds are two irregular dwarf galaxies visible to the naked eye from the southern hemisphere. They orbit the Milky Way at a distance of about 160,000 to 200,000 light-years, trailing behind a stream of gas and stars known as the Magellanic Stream. Some recent observations have led researchers to suggest that the Large Magellanic Cloud might collide with the Milky Way in about 2 billion years, which could trigger a burst of star formation and potentially affect the supermassive black hole at the galactic center. However, orbital predictions over such vast timescales remain inherently uncertain. But the most dramatic merger is yet to come. About 4 to 5 billion years from now, the Milky Way and the Andromeda galaxy will collide. Andromeda, also known as M31, is the nearest large spiral galaxy to the Milky Way, located about 2.5 million light-years away. It is slightly larger than the Milky Way, containing roughly 1 trillion stars compared to our 200 to 400 billion. For decades, astronomers have known that Andromeda is moving toward us at a speed of about 110 kilometers per second, or roughly 400,000 kilometers per hour. But only recently, with precise measurements from the Hubble Space Telescope, have scientists confirmed that the two galaxies are on a collision course. Should the collision occur, it will unfold over billions of years, with the two galaxies making several close passes before finally merging. Computer simulations suggest the first encounter could happen in about 4 to 5 billion years, when Andromeda and the Milky Way would sweep past each other, their gravity pulling stars and gas into long, stretching tidal tails. If this happens, the sky would be transformed. Andromeda, currently a faint smudge in the night sky, would grow larger and brighter, eventually spanning the horizon like a cosmic rainbow. The Milky Way would appear distorted, warped by Andromeda's gravitational pull. During a first close approach, models indicate star formation would likely surge as gas clouds collide and compress, igniting new stellar nurseries across both galaxies. The night sky would blaze with the light of young, hot stars and glowing nebulae. But individual stars would not collide. The distances between stars are so vast that the chance of even two stars hitting each other is negligible. Instead, the stars would pass through each other like ghosts, their paths altered by gravity, but their physical integrity intact. After the first pass, the two galaxies would swing away from each other, only to be pulled back together by gravity. They would make a second pass, and then a third, each time losing energy and angular momentum. Eventually, current estimates suggest somewhere between and 10 billion years from now, the two galaxies would merge, completely, forming what could become a single giant elliptical galaxy. Astronomers have playfully nicknamed this possible future galaxy Milkomeda, or Milkdromeda. Should the merger proceed to completion, it would fundamentally change the structure of both galaxies. The spiral arms would likely be destroyed, replaced by a more chaotic, elliptical distribution of stars. The supermassive black holes at the centers of the Milky Way and Andromeda would, over millions of years, spiral toward each other, and current models suggest they would eventually merge into a single, even more massive, black hole. This final coalescence would release gravitational waves with tremendous power, ripples in spacetime that would propagate across the universe at the speed of light. What would happen to the Sun and Earth during such a merger? Based on simulations, the odds of the solar system being directly affected appear low. Most likely, the Sun and its planets would be flung into a new orbit within the merged galaxy, perhaps farther from the center than they are now. There is a small probability, simulations suggest around 12%, that the solar system could be ejected entirely, cast out into the darkness of intergalactic space. But even if this were to happen, the Sun would continue to shine, and the planets would continue to orbit, now adrift in the void between galaxies. Of course, should such a merger occur, by that time the Earth will no longer be habitable. Current models predict that in about 1 to 2 billion years, the Sun's increasing luminosity will trigger a runaway greenhouse effect, boiling away the oceans and sterilizing the planet. Any life that might remain would need to seek refuge elsewhere, perhaps on other worlds or in space itself. However, recent research published in 2025 suggests that the collision may not be as certain as previously thought. When accounting for the gravitational influences of other galaxies in the local group, particularly the Triangulum Galaxy, M33, and the Large Magellanic Cloud, some models indicate there could be roughly a 50% chance that the Milky Way and Andromeda will avoid a direct collision over the next 10 billion years. They may instead pass each other at a distance, their interactions less dramatic than once predicted. The future, it seems, is less certain than earlier studies had suggested, reminding us that predictions over such vast timescales are inherently challenging. Regardless of the timing, the Milky Way's history of mergers reminds us that galaxies are not static structures. They are dynamic, evolving systems, constantly shaped by collisions and interactions with their neighbors. The Milky Way we see today is the product of countless mergers and accretions, a patchwork quilt stitched together from the remnants of smaller galaxies. And in the far future, it will merge again, becoming part of an even larger structure. The galaxy is not eternal. It is a transient form, a temporary arrangement of stars and gas that will one day be transformed into something new. And in that transformation lies the ongoing story of the cosmos: creation, destruction, and rebirth, played out over billions of years. The chemistry of existence. Every element in your body, save for hydrogen, was created inside a star. The oxygen you breathe, the carbon that forms your cells, the calcium in your bones, the iron in your blood, all of it was forged in the nuclear furnaces of stars billions of years ago. You are, quite literally, made of stardust. Not in a poetic sense, but as a matter of verifiable fact. The story of how this happened is one of the most beautiful narratives in all of science. It begins with the Big Bang, the moment 13.8 billion years ago when the universe emerged from a state of unimaginable density and temperature. In the first few minutes after the Big Bang, the universe was a hot, dense soup of protons, neutrons, and electrons. As it expanded and cooled, these particles began to combine, forming the simplest elements: hydrogen, helium, and trace amounts of lithium. That was all. No carbon, no oxygen, no iron. Just the lightest elements, the building blocks of everything that would come later. For hundreds of millions of years, the universe remained dark, filled only with clouds of hydrogen and helium drifting through space. But then, gravity began to pull these clouds together. The first stars ignited, blazing brightly in the primordial darkness. These early stars were massive, perhaps hundreds of times the mass of the Sun, and they burned hot and fast, fusing hydrogen into helium in their cores. But stars do not stop there. When the hydrogen in a star's core is exhausted, the core contracts, heating up until helium can fuse into heavier elements, carbon and oxygen. In the most massive stars, this process continues, creating neon, magnesium, silicon, and eventually iron. Each fusion reaction releases energy, but by the time a star reaches iron, the chain stops. Fusing iron requires energy rather than releasing it, so the core can no longer support itself. It collapses, triggering a supernova explosion that tears the star apart and scatters its newly created elements into space. These supernova explosions are the universe's alchemists. They not only create heavy elements, but also distribute them across vast regions of space, enriching the gas clouds from which the next generation of stars will form. Over billions of years, this process has repeated countless times, gradually increasing the concentration of heavy elements, what astronomers call metals, in the interstellar medium. The Milky Way's chemical evolution is written in the spectra of its stars. By analyzing the light from a star, astronomers can determine its chemical composition, identifying the abundance of different elements in its atmosphere. Stars that formed early in the galaxy's history, when the interstellar medium was still relatively pure, have very low metal content. These are called population stars, and they are found primarily in the galactic halo and globular clusters. They are ancient, some more than 12 billion years old, and their chemistry reflects a time when the universe had experienced only a few generations of stars. In contrast, stars that formed more recently, including the Sun, have much higher metal content. These population Y stars formed from gas clouds enriched by countless supernovae. The Sun itself contains about 2% metals by mass, a seemingly small amount, but one that makes all the difference. Without those heavy elements, rocky planets like Earth could not exist. There would be no silicon for rocks, no iron for a planetary core, no carbon for organic molecules. Life, at least as we know it, would be impossible. Gaia's data has allowed astronomers to create the most detailed chemical map of the Milky Way ever made. By measuring the spectra of millions of stars, Gaia has revealed patterns in the distribution of elements across the galaxy. Stars near the galactic center and within the disk tend to be richer in metals, while stars in the halo and outer regions are more metal-poor. This gradient reflects the galaxy's history of star formation and chemical enrichment, with the inner regions experiencing more intense star formation and thus more rapid enrichment. But the chemical story of the Milky Way is more complex than a simple gradient. Different regions of the galaxy have different chemical signatures, shaped by local variations in star formation, supernova rates, and gas flows. Some stars have unusually high abundances of certain elements, suggesting they formed in regions where a particular type of supernova or stellar process dominated. By studying these chemical signatures, astronomers can trace the history of different parts of the galaxy, identifying streams of stars that were once part of smaller galaxies now absorbed by the Milky Way. The iron in your blood, for instance, was likely created in a Type Ia supernova, an explosion that occurs when a white dwarf star in a binary system accretes too much matter from its companion and detonates. The carbon in your cells came from the fusion of helium in the cores of intermediate mass stars, which later shed their outer layers as planetary nebulae. The oxygen you breathe was forged in the cores of massive stars before being expelled in supernova explosions. Every atom in your body has a story. It began in the heart of a star, was scattered across space by a violent death, drifted through the interstellar medium for millions of years, and eventually found its way into the molecular cloud that collapsed to form the Sun and the solar system. From there, it was incorporated into the disk of gas and dust around the young Sun, accreting into planetesimals, colliding and merging until it became part of the Earth. And from the Earth, through billions of years of geological and biological processes, it found its way into you. This is the profound connection between stars and life. We are not separate from the cosmos. We are part of it, woven from the same material, shaped by the same processes. The calcium in your bones was once in a star. The hydrogen in your DNA was formed in the Big Bang. The atoms that make up your body have existed for billions of years, cycling through stars and space, planets and life, death and rebirth. The Milky Way is not just a collection of stars. It is a giant chemical factory, continuously transforming simple elements into complex ones, distributing them across its vast expanse, and allowing them to combine in new and unexpected ways. And somewhere in that process, life emerged. Carbon-based, oxygen-breathing, iron-carrying life, made from the ashes of ancient stars. You are a walking testament to the chemical evolution of the galaxy. You are stardust given form, consciousness, and the ability to look up at the night sky and wonder at the stars that made you. Gaia's revolutionary eye. For most of human history, our understanding of the Milky Way was limited by a simple problem. We live inside it. Trying to map the galaxy from our position within the disk is like trying to draw a map of a forest while standing in the middle of it. The view is obscured by trees. The horizon is limited. For centuries, astronomers could only guess at the galaxy's true shape and size. But in the last few decades, a revolution has occurred. Thanks to a mission called Gaia, we are finally able to see the Milky Way in 3 dimensions, mapping the positions, distances, and motions of stars with unprecedented precision. Gaia is a space telescope. Launched by the European Space Agency in December 2013, it orbits the Sun at a point about 1.5 million kilometers from Earth, shielded from the Sun's light. From this vantage point, it can observe the sky without interference. Its mission is both simple and extraordinarily ambitious: to measure the positions and motions of as many stars as possible, creating the most detailed map of the Milky Way ever made. Between 2014 and 2024, Gaia scanned the sky again and again, measuring the positions of nearly 2 billion stars, about 1% of all the stars in the galaxy. But Gaia does more than just take snapshots. It measures how stars move across the sky over time. By observing the same stars multiple times over the course of years, Gaia can detect tiny shifts in their positions, revealing their motion through space. It also measures distance. By observing how a star's position appears to shift as the Earth orbits the Sun, a technique called parallax, astronomers can calculate how far away the star is. For stars within a few thousand light-years of the Sun, Gaia's distance measurements are precise to within a few percent. The data Gaia has collected is staggering. A three-dimensional map of the Milky Way showing not only where stars are, but also how fast they are moving and in what direction. This information has revolutionized our understanding of the galaxy's structure and dynamics. One of Gaia's most significant discoveries involves stellar streams, long, thin ribbons of stars stretched across the sky. These streams are the remnants of smaller galaxies and star clusters that have been torn apart by the Milky Way's gravity, like threads pulled from an old tapestry. By tracing the paths of these streams, astronomers can reconstruct the history of past mergers and interactions, revealing the Milky Way's violent past. Gaia has also mapped the motions of stars within the galactic disk, revealing complex patterns and structures that were previously unknown. Stars do not move randomly. They form coherent groups with similar velocities, moving together through space like schools of fish. Some of these groups are associated with spiral arms. Others are the remnants of ancient disturbances. Perhaps most surprisingly, Gaia has detected ripples in the galactic disk, wave-like patterns in the distribution and motion of stars. These ripples appear to have been triggered by past disturbances, possibly from the passage of the Sagittarius dwarf galaxy through the disk or from the gravitational influence of the galactic bar. Whatever their precise cause, they reveal that the Milky Way is not a static, unchanging structure. It is a dynamic system, constantly responding to internal and external forces. Gaia's chemical maps have also provided new insights into the galaxy's history. By measuring the light from millions of stars, Gaia has revealed the distribution of chemical elements across the Milky Way, showing how different regions of the galaxy have been enriched by different generations of stars. Stars near the galactic center are generally richer in heavy elements. Stars in the halo are more metal-poor, reflecting their ancient origins. One of the most remarkable discoveries involves ancient stellar populations, stars that formed more than 12 billion years ago, shortly after the Big Bang. These stars are among the oldest in the galaxy. Their chemistry and motion provide clues to the conditions in the early universe. Gaia has even discovered streams of stars, named Shakti and Shiva, that formed during the galaxy's infancy and have been moving together ever since. Ancient travelers, carrying memories of a younger cosmos. Gaia has also revolutionized the study of star-forming regions. By measuring how light from stars is dimmed by dust, Gaia can infer the location and density of dust clouds, revealing the structure of regions where new stars are being born. These maps have shown that stellar nurseries are not simple, uniform clouds. They are complex, dynamic environments with cavities, filaments, and streams of gas carved out by the radiation and winds of massive young stars. The mission has even detected starquakes, oscillations on the surfaces of stars that change their shapes. These oscillations provide information about the interior structure of stars, much like seismologists use earthquakes to study the interior of the Earth. Gaia was not originally designed to detect starquakes, but the quality of its data is so high that it has been able to observe these subtle phenomena in thousands of stars. Gaia's impact extends far beyond the Milky Way. The mission has also observed millions of galaxies and quasars beyond our own. It has detected thousands of asteroids within the solar system. It has even identified candidate extrasolar planets, revealing the presence of unseen companions around distant stars. In many ways, Gaia has transformed the study of the Milky Way from a largely qualitative endeavor into a precise science. Astronomers can now measure the properties of stars with accuracies that were unimaginable just a few decades ago. They can trace the motions of stars backward in time, reconstructing the history of the galaxy over billions of years. They can identify streams and structures that reveal the galaxy's past collisions and mergers. Gaia has shown us that the Milky Way is far more complex and dynamic than we ever imagined. It is not a simple spiral. It is a layered, evolving structure, shaped by countless processes: star formation, supernova explosions, galactic mergers, and the invisible influence of dark matter. It is a galaxy with a history, a present, and a future, all written in the motion and chemistry of its stars. And we, living within it, are finally learning to read that story. The interconnected cosmos. As we have drifted through these 100 facts, a pattern has emerged. The Milky Way is not a collection of isolated objects, but a web of connections. Each thread linking stars, gas, dust, and the unseen dark matter that holds it all together. Every star's motion is influenced by the gravity of its neighbors. Every element in the periodic table was forged in the heart of a star and scattered by its death. Every galaxy we see, including our own, is shaped by its interactions with others. The galaxy is ancient, over 13 billion years old, formed from the primordial clouds of hydrogen and helium left behind by the Big Bang. Its oldest stars, found in the halo and globular clusters, are nearly as old as the universe itself, witnesses to a time when galaxies were still young and the first structures were taking shape. The galaxy is vast, stretching 100,000 light-years across, perhaps 10 times that when the dark matter halo is included. It contains hundreds of billions of stars, each one a potential sun. Many with their own families of planets. The galaxy is dynamic, constantly in motion. It rotates, not as a solid wheel, but as a fluid, different parts moving at different speeds. Stars orbit the center, some in orderly circles, others in chaotic ellipses. The galaxy is interconnected. Stars are born from molecular clouds enriched by the deaths of previous generations. Supernovae scatter heavy elements across vast distances, seeding new star-forming regions with the ingredients for rocky planets. And ultimately, life. The galaxy is our home. Not just the Earth, not just the solar system, but the entire Milky Way. We are galactic citizens, bound to the fate of this vast spiral. The light from distant stars takes thousands of years to reach us, carrying information about the past. The heavy elements in our bodies were created in stars that exploded billions of years ago. Their atoms now part of living beings who can look back and understand their origins. We have learned that the galaxy is shaped by dark matter, an invisible substance that outweighs ordinary matter by a factor of 10 or more. We have learned that at the center lies Sagittarius A, a supermassive black hole whose gravity influences the motion of stars across the bulge. We have learned that the galaxy has consumed dozens of smaller galaxies over its lifetime, absorbing their stars, scattering their remnants into the halo. We have learned that stars are born in cold, dark molecular clouds, that they live for millions or billions of years, fusing hydrogen into helium and heavier elements, until they exhaust their fuel and die, either fading away as white dwarfs or exploding as supernovae. We have learned that missions like Gaia are revolutionizing our understanding, mapping the positions and motions of billions of stars with unprecedented precision, revealing streams, ripples, and structures that tell the galaxy's dynamic history. And yet, for all we have learned, there is still so much we do not know. What is dark matter? How did the first stars form? How common is life in the galaxy? Are we alone? Or are there other civilizations out there, looking up at the same stars and wondering the same questions? The Milky Way is a vast, ancient, and beautiful structure, and we are part of it. Every breath we take, every heartbeat, every thought, all of it is woven from the same material that makes up the stars. We are not separate from the galaxy. We are of it, children of the cosmos, made from stardust and shaped by billions of years of cosmic evolution. And tonight, as you drift toward sleep, know that you are floating through space on a small planet, orbiting a modest star within a vast spiral of light and darkness. Know that you are part of something immense, something ancient, something beautiful. Know that the galaxy is turning, and you are turning with it, carried along by forces too vast to see, but too powerful to escape. You are home, in the Milky Way, in the cosmos, in the quiet, luminous spiral that made you. Closing reflection. And now the stars begin to dim behind your thoughts. We have drifted together through the grand architecture of the Milky Way, from its spiral arms to its dark matter halo, from the supermassive black hole at its heart to the stellar nurseries where new suns are born. We have traced the solar system's journey around the galactic center, circling once every 230 million years. We have remembered the ancient collisions that shaped the galaxy and looked ahead to the future merger with Andromeda, billions of years from now. We have explored the chemistry of existence, the elements forged in stars and scattered across space, the atoms that now form your body. We have marveled at the precision of the Gaia mission, mapping billions of stars and revealing the galaxy's structure in unprecedented detail. We have seen that the Milky Way is not a static backdrop, but a dynamic, evolving system, constantly shaped by forces seen and unseen. But more than facts and figures, we have touched something deeper, the realization that you are not separate from the cosmos, but a part of it. That the calcium in your bones was created in a supernova billions of years ago. That the iron in your blood was forged in the heart of a dying star. That the very atoms that make you who you are have journeyed through the galaxy for eons, cycling through stars and planets, gas and dust, until they found their way to you. You are a participant in the galaxy's story, not just an observer. You are made of the same material as the stars, shaped by the same forces, bound by the same gravity. You are a temporary arrangement of atoms that have existed since the beginning of the universe. Atoms that will continue to exist long after you are gone, cycling through new forms, new stars, new worlds. And in this realization, there is a kind of peace, a sense of connection to something larger than yourself, a quiet awareness that you are home, not just on Earth, but in the galaxy, in the cosmos, in the vast and luminous spiral that cradles us all. The Milky Way is still turning. Stars are still being born. Light is still traveling across the void. And you are part of it, floating on a small planet in a quiet corner of the galaxy, resting beneath a blanket of stars. If you happen to still be awake, you can go ahead and listen to the next chapter now. But if not, I hope you sleep well and dream softly. Dream of stars and spirals, of ancient collisions and future mergers, of the quiet beauty of a galaxy in motion. Thank you for drifting with me through the Milky Way. If these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Good night, and may the stars watch over you as you rest in the spiral arms of home.